Hi, everybody. This part of the notes is really just to kind of sum up all the different rules that we have for deciding if a series converges or diverges. I think that it's helpful in general to keep in mind what our goal is here. If a series is going to converge, that means that we're adding up numbers we're adding an infinite list of numbers that have a finite answer, which sounds really weird, but the only way it ever works is if the numbers in the list are getting so tiny, so infinitely small that they're practically zero. So when I'm trying to figure out if a series converges, I'm really trying to find out, do the terms get closer and closer to zero? If they do, then it will converge. And if they don't, well, if they do, it will usually converge. If they don't, then it will definitely diverge. So how can I tell? Well, one of the most common that you will use is geometric. When you're multiplying by the same number over and over, if the number you're multiplying by, if the absolute value of the number you're multiplying by is less than 1, then the series will be convergent. Because think about it, if you're multiplying by a number bigger than 1, what's happening to your numbers? They're getting bigger and bigger and bigger. You're adding bigger numbers onto other bigger numbers. That's just going to increase forever. So that would be a divergent series. P series is not as common, but it's similar. It's when you've got 1 on top. You have to have 1 on top. If you don't have 1 on top, then factor it out. You have the number on bottom is changing, and you have an exponent that stays the same. So that would be like 1 over n cubed. If the exponent is bigger than 1, then the series will converge. And if the exponent is between 0 and 1, then it will converge. The ones to watch out for here are like 1 over n, because that's 1 over n to the first power. Exponent is 1, divergent. Or a variation of that is if you have 1 over anything that's linear. If you have 1 over a linear function, that is also like to the first power, essentially, and that is also always going to be divergent. Telescoping, these don't happen all that often. When they do happen, it's probably because you had a denominator that you could factor, and you could do partial fractions. The thing with these that makes them so unusual is the terms have to cancel out. So I can't just have plus minus plus minus plus minus. I have to have like plus a half minus a half plus a third minus a third, and on and on and on. So the terms have to cancel each other out. If they don't, it's not telescoping. Alternating signs. The alternating signs part of this, we see that in several different things, but the part that makes the signs flip back and forth is kind of irrelevant. It's not really about the sign of the number, it's about the absolute value of the number. And are the terms getting smaller? If the term that came last is smaller than the term that came before it. So this would be like if term number 8 is smaller than term number 7. If term number 7 is smaller than 6. If term 6 is smaller than 5. Well, then what's happening to the terms? They're getting smaller and smaller and smaller, which means it's going to converge. So one thing you'll notice with alternating when you see this pattern in some of the functions, it can also be combined with other things. Are the terms getting smaller? If they are, it converges. What if it's not super obvious if the terms are getting smaller? Well, you can have alternating signs combined with a geometric, or alternating signs combined with a p-series. So alternating sign can be a thing by itself. It can also be part of something else. Other than geometric, maybe even more than geometric, the one that I think gets used the most is the ratio test. And the ratio test says take the n plus 1 term, the nth term, and divide them. And if you divide the two, and you get something that's less than 1. Okay, how can I divide two numbers and get a little answer? Well, I divide two numbers and get a little answer when I do a small number divided by a big number. So, wait, you're saying the term that came last is smaller than the term that came before it? That sounds like something we've said before. So this is literally the same thing we've said, just a different way to show that it's going to happen. So this one, you're going to see that a lot. We're also going to use that in the next section when we talk about power series. So what if the number is bigger than 1? Well, that means that we had a big number on top and a small number on bottom. That means the terms were getting bigger. That's not what you want. That's divergent. Watch out for the equals 1. If it equals 1, then that really doesn't tell you anything. It doesn't tell you it works, but it doesn't tell you it doesn't work. So that means that you're going to have to try to find something else. The limit comparison, that's kind of the, like, comparing two functions together. If I know that, it's kind of like the direct comparison test. If I know that one is, sorry, lost my words for a second. If I know that one is divergent or I know the other is convergent, then how does that affect the function? So what's happening here is I'm going to take my problem and I'm going to divide it by something that I know converges. So if you can do that and get a limit, then it's convergent. And if you divide it by something that is divergent, then the whole thing is divergent. We haven't really used that one. I don't think we've used that one at all. The integral test, we have used a few times. It basically says to do the integral, and if the integral has a limit or has a value, then the series is going to have a value. So it's going to exist. It's going to converge. If the integral is infinite, then the series is not going to converge. The series would also be infinite and not converge. Nth root test, haven't used that. Direct comparison, have used that a little bit. Basically, that's saying if I can find a function that's bigger than my function and that function converges, then anything smaller than it is also going to converge. The flip side of that is if I find a function that's bigger than my function and it diverges, then anything bigger than it is also going to diverge. So if it's smaller than a convergent series or bigger than a divergent series. So here are some examples. This is everything all mixed together. We're not going through this like one thing at a time. That's going to take too long. So when you look at these, how do you know what strategy to use? Well, a little bit of it is guess and check, but there are some things to look for. So when I look at this whole page really as a group, when I see factorials, factorials are a dead giveaway that this is going to be a ratio test. So I'm going to plug in n plus 1 for the n's. And n plus 1 is n plus 2. And then I'm going to plug in n for the n's. And I'm going to keep change flip. And when I do that, then what happens is I get a whole bunch of stuff that cancels out. So you have to kind of use a little bit of reasoning here to figure out how all this stuff cancels out. But basically what happens, trying to erase some of this so I can rewrite it for you guys. What's really happening here is I've got, sorry, trying to switch colors. This would be, when I compare those, the one on top would be like 3 to the 8th, and the one on bottom would be like 3 to the 7th, or 3 to the 3rd over 3 squared. So basically the top has one more 3 than the bottom does. So all of those 3s are on bottom are going to cancel out all but one of those on top. So there's a 3 left on top. This is like 5 times 4 times 3 times 2 times 1. This would be like 6 times 5 times 4 times 3 times 2 times 1. So all of these numbers that are in and less are going to cancel out all of these that are in and less, but the n plus 1 is not going to get canceled out. Everything below it will, but not the n plus 1. If you look over here, this has one more term than this does. So n plus 1 on down is going to cancel out. N plus 2 is not going to cancel out, but everything below it will. So then when you look at what's left, I've got a 3 on top, an n plus 1 on top, and n plus 2 on bottom. And when you find the limit as n approaches infinity of the absolute value of that, you would have 3n over n, which is 3. Okay, that basically means that my terms are getting 3 times bigger every time I add another term. So if the terms are getting 3 times bigger, I'm adding bigger and bigger numbers. That doesn't work. So that series diverges. When I scroll through some more, I'm looking for some things that kind of stand out to me. I've got all numbers, weird symbols, but numbers, and I've got an exponent. So that's a geometric series. So what am I multiplying by over and over and over and over? Well, whatever that is. So 2 pi over pi plus e is bigger than 1. If you have to type that in the calculator, that's okay, I guess. But 2 times 3.14, and then like 2.7 something plus 3.14 is like 5.84-ish. So 6 over 8 is less than 1. No, I said that wrong. I gotta fix that. Sorry, I said it wrong. 2 times 3.14 and 3.14 plus 2.7 or so is 5.84. Number on top is bigger. That's bigger than 1. So if you've got a geometric series and the ratio is bigger than 1, divergent. This one got a little bit creative. Remember on P series I said that the number on top has to be 1. So when you guys look at this, you've got a 12 on top and a 7 on bottom, and then you've got a cubed root of n. I can rewrite the cubed root of n, square root of n cubed as n to the 3 halves, but what about the 12 and the 7? Well, you can basically just factor it out. So if I have like 2 times 1 plus 2 times 2 plus 2 times 3, couldn't I just add the 1, 2, and 3 together and then double the answer? That's what's happening here. I can add all those numbers together and then multiply them by 12 over 7 at the end of everything. So, sorry, my dog found her squeaky toy. So that makes this a P series. P is bigger than 1. If P is bigger than 1, that's a good thing. That's a convergent series. Factorial. That's going to be do n plus 1 and the n, see what all cancels out. So the 4's on bottom canceled out all but one of the 4's on top. Can't really see some of this stuff. And what canceled from where. So let me see what I can do about that. Okay, so the 4's on bottom all canceled out. And we have one of the 4's left on top. The n to the 4th, this is written different ways in some of the notes and some of the different things I've seen. Are n to the 4th and n plus 1 to the 4th the same thing? No, they're not. That would be like 3 to the 4th and 4 to the 4th, definitely not the same number. But remember, we're not talking about when n is really small, like 2 or 3 or 4. We're talking about when n is infinity. So infinity to the 4th and infinity plus 1 to the 4th are both infinitely big. So when n is infinitely large, those two numbers are essentially the same. So they're going to kind of cancel each other out. Also, the n factorial is going to cancel out everything except the n plus 1. So we're left with 4 over n plus 1. And as n approaches infinity, that approaches 0. So that means when I divide the two terms, I get a very small number that's less than 1. So that's a convergent series. Trying to think of which ones I haven't done yet. This one. So what I notice about this one is that I've got those that are both, I've got 4n and 2n, and then the plus 100 is not really relevant because we're really only looking at stuff that has the variable. If I do the limit as n approaches infinity of that, 4n over 2n is essentially 2. And then when you plug in infinity, that would be 2 to the infinity power. That's infinity. That's the nth term test. And the nth term test tells us that if the terms approach 0, it converges. Well, this doesn't. So that's a divergent series. On this one, what caught my eye, anytime I see natural log, that makes me think of like the derivative of, or the antiderivative of, or u substitution, sorry y'all. When I look at this and I see natural log of something, what's the derivative of natural log? Well, the derivative of natural log is 1 over itself, 1 over whatever you're doing the log of. So if I think of natural log as u, then 1 over that, the n plus 1 would be du. So basically this is a u to the negative 1/2 du kind of pattern. That means I can do the integral of this. I can do the antiderivative. So the integral of u to the negative 1/2 du, add 1 to the exponent, divide by the new exponent. So that's going to be 2 natural log of n plus 1 to the 1/2. And when you evaluate from that from 1 to infinity, infinity plus 1 is infinity. Let's see, natural log of that is infinity. Square root of infinity is infinity. Times 2 is infinity. So the integral does not exist because the integral is infinity. If the integral doesn't exist, the sum doesn't exist. So that's a divergent series. The integral test ones are basically ones where you just have to get used to looking for patterns where you have a function and its derivative. We talked about that one. This one was, so we've got alternating signs here, but the alternating signs part isn't what really matters. The rest of it is. So are these terms getting smaller and smaller? Is n plus, if I plug in n plus 1 and then work it out, is that smaller than when I just plug in n? So you could do this a couple of different ways. Didn't mean to erase that. The limit of these terms is 0. This one does converge. That's kind of you can't really use the nth term test to say that something converges. You could have done the integral here, the integral test. Couple of different things. Sorry, I'm rambling about that one, but it converges. This one, I haven't shown you one like this. When you look at this, I've got 1 over n squared plus 4, and I know the plus 4 is not really a big deal, but if that were just 1 over n squared, that would be a p-series. And I know how to do that. So how do these two things relate to each other? Okay, well, n plus 4 is bigger than n. So what happens when I divide by a big number? I get a smaller answer. So 1 over n squared plus 4 is going to be smaller than 1 over n squared. Okay, 1 over n squared is a p-series. P is equal to 2. 2 is bigger than 1, so that converges. So I've got a function that converges, and I've got another function that's even smaller. So if these numbers are small enough to converge, then what's going to happen with the ones that are even smaller? They're also going to converge. So I hope that kind of helped explain all the different types. And I've also worked out some of the homework problems if you want to look through those. I'm also going to post those on Classroom. Probably not for a grade, but for practice. These are really good practice problems. And hope that helped sum up all the series stuff.